The queuing theory. Queuing theory is the mathematical study of waiting lines or queues. Here, a queue means a line or sequence of people or vehicles awaiting their turn to be attended to or to proceed, indicating the actual lines excluding servers. The founder of queuing theory is Agner Kurup Erlang, a Danish mathematician. He began developing queuing theory in 1909 in Copenhagen, Denmark, to analyze the efficiency of telephone networks. Erlang was particularly interested in mathematically analyzing call volume and waiting times in telephone exchange systems. His work was summarized in the 1917 paper, The Theory of Probabilities and Telephone Conversations, which became the foundation of modern queuing theory. In simple terms, queuing theory helps us understand how systems handle incoming requests and provides ways to optimize factors like wait time, queue length, and service efficiency. For instance, think of the line at a coffee shop. Queuing theory can help determine the ideal number of baristas needed to serve customers efficiently. Another example is in call centers, where queuing theory is used to minimize wait times and determine the necessary number of operators. Queuing theory comes in various forms, which we refer to as models. These models can vary based on factors such as number of servers, like in the MMC model, the randomness in arrival patterns, shown in the MG1 model, or even scenarios with an infinite number of servers, offering unlimited service, as in the Infinite model. However, all models start with the most basic model, which will be our main focus in this video, the MM1 model. The MM1 model represents a single server queue with regular arrivals. All customers who arrive from a single line and the server processes them one by one, following a first-come, first-served FCFS rule. Here, the arrival rate, or the average number of arrivals per hour, follows a Poisson distribution and is represented by the lambda, while the service rate, or the average number of customers served per hour, follows an exponential distribution and is represented by a mu. Using the MM1 model, we can quickly calculate performance metrics in various real-life settings like supermarkets, factories, and schools. Let's take Santa making toys as an example. Here are some key performance metrics. This shows the percentage of time the system is in use relative to its capacity. We calculate it as lambda over mu. Average number in the system. This represents the total number of customers in the system, including those waiting in the queue and those being served, calculated as lambda over mu minus lambda. Average number in queue. This is the average number of customers waiting in the queue and is calculated as lambda powered by 2 over mu times mu minus lambda. Average time in system. This is the total time a customer spends in the system, including both waiting and service time, calculated as 1 over mu minus lambda. Average waiting time in queue. This is the average time spent waiting in the queue, calculated as lambda over mu times mu minus lambda. Now back to the example. Let's put this into our example. If Santa receives, on average, 10 raw materials per hour, and each toy assembly takes about 5 minutes, then the arrival rate, lambda, is 10 materials per hour. And Santa can complete 12 toys per hour, so the service rate, which is the mu, is 12. Using lambda and mu, our calculations reveal average number of items in the system, 5 items. Average number of items waiting in the queue, approximately 4.17 items. Average time in the system, 30 minutes. Average wait time in the queue, approximately 25 minutes. Utilization, approximately 83.3%. This means that on average, 5 raw materials remain in Santa's factory at the same time, with approximately 4.17 items waiting in the queue. Each raw material spends an average total of 30 minutes, 0.5 hours, in the system, including an average of 25 minutes, 0.416 hours, waiting in the queue. The factory system operates at approximately 83% utilization. Another example could be people waiting to use the restroom. At a tourist site with a single public restroom, an average of 13 people visit per hour, and each person uses a restroom for 5 minutes. In this case, the arrival rate, which is the lambda, is 13 people per hour, while the number of people who can use the restroom per hour is 12, making the service rate, which is the mu, 12 people per hour. However, if we use these values for lambda and mu to calculate the performance metrics, the average number of items in the system, the average number of items waiting in the queue, the average time in the system, and the average wait time in the queue, the results will differ from what the MM1 model predicts. In the MM1 model, the performance metrics can only be calculated if the inequality is lambda is less than mu. In this restroom example, with lambda being 13 people per hour and mu being 12 people per hour, lambda is greater or equal to mu, resulting in 108% utilization and indicating an unstable system. This suggests that theoretically the queue length could grow infinitely. This system issue can be resolved by either reducing the arrival rate, the lambda, or increasing the service rate, the mu, by adding more restrooms or optimizing usage time. However, since the MM1 model is the simplest queuing model, it does not account for human factors such as psychological behavior, meaning variables can change anytime. These performance metrics gives us insights into how efficiently the model operates. The data helps company managers decide whether they need to adjust the arrival rate, increase the service rate, or add more servers to improve efficiency. Queuing models are present in our everyday lives. For example, airports. Security checkpoints and check-in processes are designed using MMC models to process passengers as efficiently as possible. Also, in manufacturing, assembly lines rely on queuing models to manage workflow and prevent bottlenecks. Computers. CPU scheduling applies queuing theory to organize tasks with FIFO, first in, first out, being a common approach. In fact, any system that uses waiting lines can be considered an application of queuing theory. Each of these models contributes to streamlined operations, ultimately improving customer or patient satisfaction. To sum up, queuing theory provides a mathematical approach to studying waiting lines. Today, we covered some basic terms and the fundamental MM1 model, which represents single server systems. Queuing models are crucial in various industries, including retail, healthcare, and transportation, as they enable more efficient service delivery.